So I guess Ramón is now based at ICFO, but when this work was done, it was at the University of Toronto. So he's going to tell us about measuring the time tunneling atom spends within a barrier region. So please take it away, Ramón.
Hi, yes, my name is Ramón, and I'll be telling you about this tunneling time. Tunneling is one of the most well-known consequences of quantum mechanics. The problem that almost every quantum mechanics textbook describes is that of a particle incident in a square barrier. And we know that classically, if the incident of the barrier is below the barrier height, then the particle would be reflected. However, we know that this problem can be treated quantum mechanically, and we find that there is some transmission probability, and that's what we associate with tunneling. And although tunneling is well understood and used in current technology, there is a key question that remains unanswered, and that's how long does it take for a particle to tunnel? To answer this question would not only lead to a better understanding of quantum mechanics, but also it can have some applications. So in biophysics, for example, when proteins interact, they do it through different electron pathways, and some of these pathways rely on tunneling. So if we can find out that the tunneling time is longer than a certain characteristic timescale of the system, then we can ignore those pathways and simplify calculations for these kind of systems. Also, we have some devices in electronics that rely on tunneling. And although the tunneling time doesn't determine the maximum speed at which these devices work, there is a new branch known as molecular electronics, which heavily relies on tunneling. So knowing the tunneling time for this coming new technology would give us a sense of what is the ultimate timescale for these systems. So if tunneling time can have these consequences, why is it usually not studied? And the reason is because there are no trajectories in quantum mechanics. So classically, what one would do is to measure the time at which a particle enters a region, and then later on measure the time at which the particle exits that region. By taking the difference between these two times, we can obtain the duration of the particle in that particular region. However, the concept of trajectories is not well defined in quantum mechanics. So if we try to do the same measurement, we will find out that the first measurement that we do will disturb the system, and therefore whatever we obtain won't be representative of the tunneling time duration. Another approach that we can try to find out the tunneling duration is to divide the barrier width by the velocity of the atoms. However, we know that the velocity under the barrier becomes imaginary. And so this quantity that we obtain won't have a clear interpretation. So how do we actually measure the tunneling time? And that essentially follow the recipe of this picture. So imagine that we have these hedgehogs, which will be our atoms. And what we're going to do is we're going to give each of our atoms a stopwatch, such that when they enter the barrier, when they start tunneling, they can start the stopwatch. And once they exit the barrier, they can stop the stopwatch. And then on the far side of the barrier, we can interrogate the atoms. So what it means is that all we need is a clock for atoms. And this thought experiment was developed essentially by Bas and Rybachenko in the mid-60s, and it is known as the Larmor clock. So now imagine we have a particle, and this particle has a spin 1/2 that we can prepare in a superposition of up plus down along the x-axis in our Bloch sphere. We also have our barrier, and inside this barrier, we're going to localize a magnetic field that is pointing along the z-axis. So if the particle tunnels through this barrier, because there is a magnetic field localized inside the barrier, the spin of the atoms will precess, and this precession angle will tell us about the duration that the particle, the duration of the tunneling time, essentially, or the duration of the tunneling. So in a way, the spin is acting as a stopwatch where we initialize it to 0, and then later on we can read out what was the duration of this process. It was later on recognized that this is not the full story. So besides this precession angle theta y, there is another rotation angle that is along the z-axis. And this rotation angle is essentially the back action of the measurement that we're performing. In this particular case, it comes because we are introducing this magnetic field inside the barrier region. And that means that the spin up and the spin down will have slightly different tunneling probabilities. So then, using these angles, we can obtain some characteristic times just by dividing them by the Larmor frequency, which is related to the strength of the magnetic field. So tau y will tell us about the tunneling time, while tau z will tell us about the disturbance that we're casting to the system due to the measurement that we are performing. So what does this mean experimentally? It means that if we want to perform this experiment, we'll need the following ingredients. So we need a spin that will act as a stopwatch. We're going to need an ultra-cold wave packet. And this is to be able to say that all the atoms that we see past the barrier are atoms that have tunneled through the barrier and not just went over the barrier classically. We're going to need a thin barrier that allows us to see tunneling. And we're going to need something that acts as a magnetic field inside the barrier region that allows us to couple the different spin states. On the far side of the barrier, what we want to do is to be able to do a spin tomography on the atoms that have tunneled through the barrier. Okay, so this is how our setup looks like. So we're going to work with rhodium-87 atoms in a Bose-Einstein condensate, and we're going to have a spin 1/2 system using the clock states of the ground state manifold. Our atoms will be confined in a waveguide for the atoms, so this is an attractive potential, with a radial frequency of 220 Hertz and a longitudinal frequency of around 3 Hertz. That means that all the dynamics are going to happen along the longitudinal axis, that is the y-axis. We are going to intersect our atoms with a laser beam, and this laser beam is going to act both as a barrier and as the pseudomagnetic field that will couple the spin states. This laser is focused down to around 1 micron, and this means that this is enough to see tunneling through this potential. Also, what we're going to do is we're going to choose carefully the wavelength of this laser such that we can create two situations. The first one is that we can set the barrier height V0 to 0 while keeping the strength of the magnetic field finite. This situation will allow us to characterize the Larmor clock in the case of free propagation and to make sure that everything works as we expect. Once we have essentially calibrated our Larmor clock, we're going to move to a situation where the barrier height is finite, and inside the barrier, we will also have this pseudomagnetic field present. And that's the case where we're going to perform our tunneling time measurement. So the experimental sequence will be the following. First, we'll start by cooling the atoms using a technique known as matter wave lensing, and this will allow us to obtain a temperature of around 900 picokelvin. Once we have cooled down our atoms, we're going to push our atoms toward barrier and this pseudomagnetic field. One thing to notice is that initially all our atoms are in the F is equal to 2, M is equal to 2 state of the rubidium hyperfine state. What we're going to do next is we're going to prepare our spin. For that, we're going to transfer all our atoms to the plus X state, which is related to the F is equal to 2, M is equal to 0 state. Once the spin preparation is over, the atoms will arrive and they will interact with the barrier and the pseudomagnetic field. Because of the barrier, the atoms can either transmit or they can reflect. And because of the pseudomagnetic field that is present, the atoms can couple from the plus X state to the minus X state. Once the interaction is complete, we can perform a global spin rotation. This is to do full tomography on the spin of the atoms. And at the end, we're going to read out our atoms by applying a Stern-Gerlach sequence and taking a picture of the condensate. So this is our result. First, we're going to look at the case where the barrier vanishes, but we still have the pseudomagnetic field present in that region. So we're going to get pictures that look like this. So all of the atoms will be transmitted and none of them will be reflected because the barrier is set to 0. And because of the pseudomagnetic field, some of the atoms will couple from the plus X state to the minus X state. So if we plot our results in the block sphere, the spin initially pointing along the x-axis has precess in the xy plane. And this precession angle is essentially related to the Larmor frequency, the width of the barrier, divided by the velocity of the atoms. So our data agrees well with this prediction. So that means that we understand how our Larmor clock works. Now we can move to the case where there is a barrier present, and inside this barrier we have also the pseudomagnetic field. So in that case, we're going to get pictures that look like this. So some of the atoms are transmitted, some of the atoms are reflected, and because of the pseudomagnetic field, some of the atoms will couple from the plus X state to the minus X state. So what we want to do now is to vary the incident energy of the atoms and see what is the duration of the tunneling process. So these are our results. Our results shown in the block sphere. So first, we can take a cut of the x in the xy plane. So the rotation in the xy plane is related to the tunneling time. That's tau y. And also we can take a cut of the xz plane, and the rotation along the z axis is related to the disturbance that we cause into the system due to the measurement that we are performing. And that's tau z. So we can plot this as a function of the velocity or the energy in terms of the barrier height. And the y-axis, this is time in milliseconds. From this, we can also extract the transmission probability, which for the lowest point is around 3%. The solid lines are theory based on weak value formalism, and our data agrees well with this theory. Furthermore, we can compare our data against 1D two-component gross-Pitayevsky simulation, and again, the agreement is good. We can compare our data against a different theory for what the tunneling time should be. In particular, over here, the green line is comparing against what is known as the semi-classical theory, which is essentially the barrier width divided by the absolute value of velocity. And we can see that our data disagrees with this theory, or it rules it out by almost 3 sigma. From our data, it's important to point out that at the lowest energy that we can send and we can have a signal, we see a traversal time or a tunneling time of 0.6 milliseconds. And this is in sharp contrast with the zero tunneling time that other experiments have claimed to measure. So we think that our results answer the long-standing tunneling time question. So with this, I arrive to the summary. So this is the first tunneling time experiment with a clear theoretical interpretation. And our results show good agreement with theory and also with simulations. So we think that our results can also help to understand other systems in which it's not easy to access this tunneling time directly. Moreover, in future experiments, we want to see what happens with this tunneling time when we tune the interatomic interactions or we add dissipation to the system. Finally, I just want to point out the people involved in this project. So Ephraim Steinberg, my PhD advisor, and David Experience and Isabel Rosico, which are junior PhD students. So with this, I would like to thank you for your attention.
Well, thank you very much, Ramon. That was really fascinating, and this is really a beautiful, beautiful result. So I'm really glad you were able to tell us about it. So we have just had one question that's come in from the chat. So it's from Tom Purves, and he asks, what is the chance that an atom gets lost from the waveguide? And if they do get lost, then how do you account for this?
Okay. So the waveguide it's a potential that is really farther tuned. So the chances that we actually lose an atom from the waveguide are very small. And if for some reason it gets lost, we actually have, so this is not a single measurement. These are multiple measurements. So each point is essentially a part of around 50 measurements each. So statistically, it averages out.
Great. So you mentioned at the end here about the effect of dissipation. So could you say a couple more words on what we would expect in this case? Because I don't have any intuition here.
Yeah, no. So this is something that has been barely touched theoretically. Yeah, I think in the late 80s, Leggett made some predictions about it, but in an ideal system. So I think part of the fascination of continuing with this work with dissipative systems is because no one really knows what to expect from it. And this is mostly the case of all the systems that we have in nature, that most of them are dissipative. So yeah, we would like to see this experimentally.
Oh, very exciting. Excellent. And there's another question that's just come in from Zeno Tofano, who asks, what is the influence of the magnetic field? And could one use an electric field instead?
Okay. Yeah, so this magnetic field that I talk about is a pseudo-magnetic field. It's not a real magnetic field, because a real one is really hard to confine in a micron in a space. So what we do is, and I'll didn't touch on this, it's a two-photon transition using a pair of Raman beams that essentially act as a magnetic field. And to come to the question of could you use an electric field, you could use everything that couples the spin of the atom inside the barrier. So all you want to do is to create this kind of precession, which you can later on identify with the tunneling time.
Great, and I think we have time for one final quick question. So we have a question from Beta Cardinal, sorry if I'm saying that wrong, and it says, can the tunneling time be estimated from a current flowing in the tunneling junction?
Yeah, that's a good question. And in fact, there were experiments in the mid-90s looking at this. However, the resolution was not the greatest for these experiments, so they were not able to get to a conclusion. Yeah. But in principle, they will be able to measure something like this. Yeah.
Well, great. Well, thank you very much. Thank you for the talk. It was fascinating, and thank you for the questions.
Yeah, thank you.
Great.